So again, thanks everyone for joining. And I want to start off with giving you guys some little updates about what's currently going on. Uh, what are some of the things that I've been working on? I'm trying to work towards a zero point 0.2 release, or I guess actually this should probably be written as zero point 0.3 release. But I'm trying to do a list of things. So the first of all, I want to include a benchmark, a PNG file for all of the algorithms using Seaborn. As you guys know, the current benchmark sort of can be difficult to use. For example, you can't see the agent's performance in all of the game at once because if you do so, the browser becomes very laggy, unusable in the mobile platform. Unusable in the mobile platform, so you have to open each of them um, individually, and that could be a lot of pain sometimes. So this week I worked on this, which finally was able to generate a bunch of um, plots that are generated by matplotlib under the hood, and it's much easier to see. There's some issues with the legend, but overall, I think this is worth to have. Um, and there's second, I'm trying to maybe consider using a wrapper to replace the functions in the common.py. So in the common.py, we basically have features to handle the discrete and continuous observation space. And I was thinking maybe we could use a wrapper to do this instead. And from an implementation standpoint, it might be easier. And also, it might be useful to add a wrapper to convert everything coming out of the environment to be a torch tensor, and everything inside of everything into the environment to be from torch into numpy, so that every script we don't have to use this to device anymore, um, because sometimes that could be sort of annoying to deal with. But anyway, probably not a good idea to go down the list one by one, but just something that I think maybe we should work on for the next week. The next monthly development cycle. Instead of reading a new paper, maybe we should do something for just try to tune the algorithms, or working on the refactoring to work on a major release, which also would again benchmarking the Atari games. Um, so yeah, so that's a little update. And has anyone tried about the C51? Has anyone tried doing the implementation for it?
Not
I
yet.
have.
Who have?
I have.
Okay, nice, nice. Wait, is that Rosalind or Niju who said who did?
It's always last one.
Okay. um, yeah, Rosalind, what do you have for the updates for the C51? I also did a little implementation. But how about you? How's your results coming?
Overall, it runs really slow, but it seems like it's learning at least. So
Okay, nice, nice. Yeah, that's my experience as well. And I think maybe using GPU would help because when you do the C51, especially with Atari games, you're doing a lot of convolutional layers, and to my understanding, the GPU would significantly speed up that process.
actually, I was using the GPUs, but nevertheless, it doesn't work as fast as the original GQN.
Right, right. Yeah, there's that might be a issue on my part because Um, so I think at some point I profiled the DQN's performance, and the reason why GPU is slow is because of this two device that's sort of slowing things down. So if you look at let's say DQN, um, essentially at some point you're making the rewards transferring to the GPU device, and that's
Mhm.
taking a really long time. If you if you benchmark, if you run a profiler against the CPU what you will find is that the loss stop backward is taking the majority of the time. However, if you use a GPU, what's going to take most of the time is actually this to device. So the how you transfer the memory from CPU to GPU becomes a bottleneck rather than the gradient descent itself. So
Okay,
that
I see.
yeah, so that's why I was thinking maybe we should use a wrapper to convert everything into PyTorch, and I wonder if that's going to make the performance better because then you can kind of avoid the expensive two device, and that might speed up the GPU implementation a lot. Well,
Come again?
um,
By adding the wrapper, what's going to change exactly?
so I was thinking adding a wrapper that essentially so the gym environments it returns a numpy array usually of the observation, right?
Mm-hmm.
And what we would do is to convert that numpy array into a torch tensor.
Okay.
And then in addition, basically we want to get rid of everything that has numpy over here. So for example, this should be something like torch tensor. This should be like torch.empty. So that essentially we try to avoid the conversion cost between the CPU and the GPU.
So using NumPy instead of Torch,
No, no,
basically.
no. The opposite, using torch instead of numpy.
But isn't it the same since we still have to copy it to the GPU?
Yeah, I guess in a way, but my theory
Or
is
is it
that
because we're using the two that is making it difficult?
yeah. So my theory is that so for example, the observation rate, right? There. So currently we are creating this huge numpy array, and then putting things into it, and then extract things from it to do the optimizations. The other way to do it, which is what I'm thinking might speed up, is what if we initialize a torch tensor initially that's already on the GPU device? So every time you receive an observation, you're just putting that into the GPU device. Um, yeah, I don't know. It might not help a lot, but I feel like it might. So, but overall, I think it's going to make the implementation a little cleaner because you don't have there's not going to be any NumPy related things in the code anymore, and also you don't have to do a lot of this two device thing that's sort of making the code more difficult to read. So this will be just S rewards plus gamma times target max times one minus nonce instead of having torch.tensor two device all over the places. So yeah, yeah. My experience with the C51 has been it's kind of slow, but I ran a very preliminary experiments on Pawn, and it seems to converge after about 1.2 million steps, and it's still running. And there's also another implementation issue that I should take care of, because the current implementation is. Blows up the memory essentially. As you can see, my current system memory is very bloated. I have 62 gigabytes of RAM, and it's all used up essentially because of the single run. And my theory is that um, the C51 or anything that we have for the DQM based approach, because we have this observation array, that is 400,000 or 40,000 length and plus observation space. It's a huge memory allocation, and then you're creating a new one every time. And then Python has to garbage collect it every once in a while, and that's probably what's slowing things down. But for DQM based approach, you don't really need this observation array. It's mostly for debugging purposes in a sense. So I think removing it will make the memory requirement a lot better. Yeah, but overall, Pawn seems to perform pretty well. This is the agent's performance visually. So I think it'd be interesting if we actually take a look at what it's trying to do, right? specifically what kind of behavior it tries to learn. And I think this is what I was trying to say. Notice how the agent always does this shot, a V shot that sort of going this way and going there, right? So yeah, visually it doesn't seem to learn a very interesting strategy, but rather it just kind of follows the same pattern again and again. And that's, I would imagine, not really how human would play it, but this seems to be this pattern that the machine learns to take advantage of.
But I guess it depends on what strategy the opponent is taking.
What strategy is what?
The opponent is taking. If
Yeah, exactly.
it's able to always win with that strategy, then that's the optimal objective.
Yeah,
Yeah.
Of course, of course. The agent really should do anything that could maximize the objective. I guess the thing is that when it trains with the when you train with the Atari domains, you couldn't really add anything to configure the opponent's how it's going to behave. So that's why the agent just learns to exploit something that is very easy to defeat the default bot. But yeah, so for the implementation, you can actually go up and you can find the implementations in the CleanRL repository for now, or you can just open this run, which is available at cleanrl.casa.sh. And then you can click on the first one and then go to here, files, and then you can see the code that exactly reproduce it. And something to notice is that this wrapper is very important. Previously, I think at some point I worked with Atari before, but without using the wrapper, and the agent doesn't learn anything at all. So the wrappers are actually really important. And specifically, I think one of the wrapper, what it does is to stack 4 frames and then sort of pass 4 frames to the agent. So if you look at the implementation and you look at the input layer for the Q network, it's a frames equal to 4. So the inputs to the neural network is actually 4 frames and times other things. And the reason is that it doesn't use long short-term memory, so the agent has no way of remembering, for example, where is the pawn going to, which direction it is heading. So you actually need 4 frames to help the agent to deduce the velocity and the direction that the pawn is going. But overall, there's a lot of wrappers going on over here, and this wrapper, for the most part, is taken from TorchBeast repo, which I found to be a surprisingly easy to read implementation. I haven't read it in detail, but it just seems the core code base is very simple. It has just a few components and a TorchBeast main file that is only 600 or so long, and it does a lot of wrapping to eventually make this work. And aside from the wrapper, I think let's maybe start talking a little bit about the implementation, just to make sure that we're on the same page. And I'm going to put this on the left-hand side and the source code on the left-hand side. And let's take a look at the pseudocode. So again, the standard DQN approach is you take some actions according to some epsilon greedy exploration strategy, and that's what this epsilon is, according to some linear schedule that produces the epsilon from in the beginning of the training, the epsilon is 1, and when you go to the end of the training, the epsilon becomes 0.02, and at each time step, you generate a number from 0 to 1. And if that number is less than the epsilon, then you do exploration. Otherwise, you use the action generated by the Q network, or in this case, the network of C51. And I think it's important to talk about how you generate the first action. So, given an observation array, this is what the neural networks look like. First of all, the inputs is the frames, as well as the frames and the pixel inputs, which is the neural network, and then you pass through a ReLU layer, a convolutional layer, blah blah blah, and then eventually you flatten it, connect it with a linear layer, and then eventually what you output is the number of actions times the number of atoms, and that'll give you essentially the distribution of the returns for different actions. Now, how you would generate these actions is, first of all, you calculate the PMFs, the probability mass functions, which is essentially this part, where what you generate is the number of batch, and then the number of actions, and the number of atoms, and you apply a softmax space on it. And essentially what this produces, unfortunately, it's kind of probably not a good idea for me to keep talking on this. And I don't know, is that making much sense to you guys?
Yes, I think so. So that Q network, the output of that is the histogram of atoms, right?
Yeah. Perhaps I should try to do the implementation week better by having some sort of a notebook or demo, because I feel like maybe I wasn't doing a very good job over there. But let's take a look at maybe some of the code too. I don't know if this is gonna help you to understand. I don't know whether this is gonna help, but I'm gonna give it a try. So this is at each time set. This is observation that it's being fed in, and let's take a look at its shape. It's the shape of 4 frames, 1 batch, and 84 by 84 frames, right? And you pass it into this neural network. And first of all, what you would do is to generate the logits. And this is how you generate it. And then the logits shape is the number of actions times the number of atoms. So the number of actions is 6, and the number of atoms is 51. Or 5, sorry. The number of actions is probably 5. Or 4, sorry. Right? That's how you generate this logit. And then you create a probability mass function, and it's essentially this. And let's replace this with 51. And the PMF shape is this. And if you print it out, it becomes this. And that's essentially the probability of this action resulting in a particular return or atoms. So for example, if you execute a first action, what this number means is that if you execute the first action, there's a 2.8% probability that you're going to reach the return of a certain atom, the second atom. So that's kind of what it means. And another thing that we need to talk about is this atoms. So when we pass in the number of atoms, we also pass in the minimum v value and then the maximum v value. And when you generate the atoms, it's essentially I think it's probably easier to just print it out. But you would generate this, where this is a canonical. This is the typical return of the distribution, where the first atom means you're gonna get a return of -10, and the last item means you're gonna get a return of 10. And then it increase linearly, and that's how you set up the atoms, and this corresponds to the probability of reaching this return. So that's what those means. And in order to get the Q values, you need to multiply this probability mass function, multiply it by the atoms, so that you get, and then you sum it up so that you get the actual Q value of each action. And then the way you do it is you do this, which now what it gives you is the probability times the atoms, or the probability times the actual return, and then you sum it up.
So it's sort of an expectation. I'm sorry.
Yes, the expectation. So now that you sum it up, this gives you the actual value of the current action, of the 4 actions, let's say. Right.
How did you know to make the range -10 to 10? Is that just like a
Yes.
point based on your expected return for the type of episodes?
So that has been reported as that's the default value that's being used in a paper. So if you search for 10, it says for our study we use the DQN architecture, but output the atom probabilities instead of action values and choose Vmax equal to negative Vmin equal to 10 from preliminary. So it's a hyperparameter essentially.
I guess for different environments, you probably normalize your returns so that they look something like that. Like if you have a environment with the MVP that has a reward that's much higher than that, that wouldn't work, right?
Yeah, so that's a very interesting point, and I think we talked a little bit last week. So I think this is really saying, given the current, it's not a perfect estimate, right? Because if the maximum reward you could get is like 2,000, then by setting Vmax equal to 10, it's not clear what that means. It's almost limiting the possible return you could get, I guess.
Yeah, I guess we just truncate all the other rewards that are higher than 10.
Yeah, like, because theoretically your value really should be, on average, and if it is in pawn, the Vmax should be 20 and Vmin should be negative 20. And then if you're in something like breakout, your Vmin should be 0 and Vmax should be, I don't know, something like a couple hundred. So it's really not clear why setting such a dummy number would work. But it seems to me the intuition is in general that instead of being a very specific actual value, it means more of some sort of guidance, some sort of guiding return, that 10 just means it's really good rather than the actual value.
Is it like based on the rewards we get for the specific environment or something like that? Is the Vmin and Vmix is based on the rewards, which implies like we should know the range of the rewards before implementing DQN distributed network.
So when I said the Vmax and Vmin, I don't think they tune it for each
Okay.
Arcari environment. So they just use Vmin and Vmax for each individual environment. For every environment.
Another possibility.
Yeah, and in fact, Rosalind recommended a great video done by the professor who invented this algorithm, and I think
It was not me. It was not me.
what was that?
The video was not mine.
That was me.
Oh,
My
my bad.
So you actually get
Yeah, so Lucas recommended this
that
very good
if we look
video
at the vast
that you guys should check it out. In particular, I think at some point he did this demo. I to show you what the agent's performance look like. And he did a visualization of what the V min and V max is. Let me see if I can find it. So over here. So as you can see, the return, essentially at this point of the game, the agent is kind of expecting the return to be sort of medium. And then over here, he's talking about how if one of the enemies getting close to the ground, if they get to the ground, then you lose. Then you see there is a probability of getting 0 return, so which means you lose the game very quickly. So even though they use something like 0 to 10, range from 0 to 10, it seems to be working for all of the games essentially.
Okay.
Yeah, so very interesting visualization. And that's something.
I believe in some of the wrappers there is some function that clips the reward to either 1 or -1 or 0.
Oh, really?
So that's maybe why there's no need for such a diverse atoms anyway. Ah, wait, but it's the return we are talking about. So.
Yeah, it's a return that you were talking about.
It'd be a function of reward and episode length.
Yeah, so if you have a lot of reward, like a lot of +1 reward, it doesn't matter if you clip it, your return should still be something like 2,000 and instead of 10. So I think that's definitely some part that is not very intuitive about this particular method. But I think there's also intuitive part of it. Instead of 10 being the absolute maximum value, it's more like a temporary maximum value. That just seems to be the idea that I'm getting. But yeah, so once you multiply the PMFs and the atoms being generated, then you get this actual Q values for each actions, and then you select an action that corresponds to the largest Q value, of course. And then you essentially start training the neural network. So because of the way that we set up everything, I use a DQN template to sort of do this. So I ended up using a target network, which is not really used in the original paper, I believe, and it seems to perform just fine. But let's take a look at how it's being trained. So first of all, what you would do is you generate the PMFs, the probability mass functions given the next states, and then if we take a look at the pseudocode, we also roll this to the appropriate places. So this is essentially this part corresponds to this part. And first of all, you sample a mini batch, a transition, and then what you would do is you get the actions given the next state. In particular, notice this is xt plus 1, so it corresponds to the s sampled next observations. And then we pass it into the Q network, which calculates the PMFs. And again, it's because we generate the logits based on the next observation, and then we generate the PMFs, and then we return it. And in this case, we actually don't need the new actions that are being generated. We just need the PMFs. So that's why I just use the underscore instead of actually getting the actions. So now that we have the PMFs, we need to calculate what's the next atoms going to be, because you need to sort of adjust the atoms correspondingly to make sure that you're dealing with the same distribution. And this part is confusing to me too. So feel free to chime in if.
Exactly. This part is kind of like not clear.
Right.
As well.
Right, of course. So I think the algorithm part, when you implement it, it's kind of straightforward, but it's more of the idea that are a little arcane. So what you would do first is you modify the atoms to be this. And remember, the atoms are canonical returns, and they look like this, right? And then when you adjust them, they become this, which now I probably need to rerun it and stop over here. We actually need to run 10,000 timestamps before the learning starts. So I have to give it a little minute. So in particular, notice the next atoms is gonna look something like this, where the first one is this. And that essentially corresponds to this part, where you're getting, you're getting whatever's inside. And then you calculate the delta Z, which is this part. And remember, the delta Z is the distance between the original atoms. So you simply just use the first atom to minus the second atom, and that gives you this delta Z. And now you calculate the TZ, which is this part. You clamp based on the max and the min. And you calculate the B, which is TZ minus B.
Index.
Beg your pardon?
It's the index, right? Of the
Right.
modifier.
Yes. So in the pseudocode, they're using the index, but in actual implementation, you just use array to do the multiplication and the subtraction to be a little easier. Right. So over here, you have B. Ignoring the J is B equal to T minus V min, and then divided by delta Z. It matches over here. And over here, you're getting the lower bound, and you're getting the upper bound.
And why you need these bounds?
So it's a floor and the ceiling function, right?
Yes, but this I don't quite understand this part.
So for this part, I think something that'll really help is to take a look at this video. It tells you why they are doing this projection, right? Have you looked into this video in detail?
I watched this video, but I don't recall this part, the particular part.
At some point, he mentions why you would do the projection. Yeah. So I think especially this part, I think would be worthwhile to read, because I think this part is where he talks about why you do the projection, or where does all of these come from. But honestly, though, I haven't personally checked it out. So for the intuition that I take is that it simply sort of does the it's simply distributing the weights. So so what is this exactly? You're using the upper bound to minus bj, and then the remaining parts become distributed to the ml, and then you're using the bj to minus the lower bound to get the remaining part to be distributed to mu. So this is sort of the confusing part, and I feel like I'm probably not going to do a better job explaining why it works, and because I only get a little bit of intuition of what this is doing, and not fully understanding it, I guess. So I guess I'll probably move on for now with this problem. But then essentially, what you would do is you generate the old PMFs, which is this, and then the loss is a cross entropy loss. And that's just the target PMFs multiplied by the old PMFs log, and then you sum it up, and then you use a negative to minimize, to say this is a number that you want to minimize, and then you're taking the mean out of it. And that's essentially it for the C51. I'm sorry I couldn't give a better intuitive explanation for why this works. But yeah, this is kind of what I have.
Good job. Good job.
Yeah, good job.
Thanks.
Yeah, thanks for explaining it. Yeah.
I kind of want to come back to that part especially because I think it was the hardest part for me.
Yeah.
When they compute the L and the U by taking the floor and the seal of the big BJs, then the U is used. In the source code, I think you use the L's as indexes themselves.
Yes.
Right? That's how did we go from atoms to index of some array?
Well, because it's
tricky part.
Because it's allocating to the corresponding atoms, right?
But what does the ceiling and the floor has to do with the index instead?
Right. So, I mean, we can actually spend a little time, since we have 20 minutes or more, I think maybe it is something that we can do together. So what is this L exactly, right? So over here you get the B. What does it look like? Right. Calculate these real quick. So we get a TZ, which is essentially a clamped atoms, the clamped next atoms, I guess. And now you calculate the B, which equal to this, and to visually inspect, this is what it looks like. And what is it exactly, right? It's the next atoms minus the Vmin divided by the interval.
The next atom minus Vmin, okay?
Right.
So that kind of gives us the index of the atoms themselves, since we divide it by d delta z.
Oh, I think you're right. Yeah, it gives you the index, sort of an approximate index, right? That's why you do the floor and ceiling. Right, because
you showed us some blog, some github.io blog where there was the atoms plot. If you could bring it back, I think it could be useful.
Yeah.
Small, yes, that one, yes. So the BJ is corresponding to the yellow, not yellow, but the green point, I guess, because it's not where we defined the atoms, right?
Right. So the green one is essentially the green one is essentially the TZ over here, right?
Yes.
Right. Okay. Yeah. I think what you say definitely makes sense. So essentially, what you're trying to do over here is, if you, instead of using TZ to do this thing, if you just use the QNetworks.atoms to minus this, it's going to give you the index, the exact index, right? It's 0, 1, 2, 3, 4, 5, and goes to 50, right? And now when you do this B, it's more like an approximate index. That's why you see this 0.25 up until 49.75. And now when we do the ceiling and the floor, what it gives us is this and this, which give, right, interestingly, it's going to give us the first 50 items and the last.
Well, it
50
makes sense
items.
because if you check the reward batch, it's probably 111 everywhere. So
The reward?
yes, the rewards you have sampled like S underscore rewards.
How is
Because
that?
that's what we add to the next distribution. Well, it's even 0.
Yeah, I don't see how that would be related, right?
So it means that the target distribution of the return does not change, or maybe just with the gamma. Oh, so only the gamma.
Well,
Okay.
here you're sort of dealing with the sparse rewards. That's why you have 0, 0, 0, right? But if the only interesting case is what if it has 1, right? Well, okay. So I think this is making a lot of sense to me. You have the lower floor, and then you have the upper ceiling. And now what you're essentially trying to do is to use the upper floor minus B. And what does that give us? Let's take a look. And it makes sense. You're multiplying by the next PMFs. So what does this gives us first? What I'm gonna do is to check the first elements. So what does this give us? You use a U to minus B. Right, so the U minus B. So again, U is this over here, and then B is over here. So essentially, B is closer to 0, but there's still some components that are close to 1. So you use 1 minus 0.25 to figure out what's the part that that'll sort of belong to 1, right? And it gives you 0.75. And you multiply that by the next PMFs, which is this number. The next PMFs is the probability of ending in a particular atom. Right. So that's where the distribution comes in, right?
Indeed.
And then you're essentially distributing that distribution by using the index add. Because this B, L, U's are essentially indexes, you're adding this L and U to the corresponding target PMFs. But the thing that I'm not understanding too much is that over here, right, this U minus B part. So even though B is 0.25, it's closer to 0, but more far away to 1. However, it seems to be saying that the upper part, which has the higher portion, is 0.75, and that is multiplied by the next PMFs. I'm probably not making a lot of sense here, but it seems like it almost seems to me that they're mismatching the proportion, that you should sort of do this proportion in a reverse way. What am I missing? 0.75. Oh, right. Sorry. Yes, exactly. That's exactly what it should be. So in particular, notice over here, right? This gives you the 0.75. Remember, the B is closer to 0, right? So essentially, the target PMFs at the 0th index should be allocate more of the probability, right?
Yes, it's like augment the probability if the reward, that return is more likely, becomes more likely.
Yes, exactly. So notice for DML, which is what the lower index is going to get, is this upper part, which is a 0.75. So this 0.75 is indeed getting allocated to the 0th index.
Okay. Now I'm curious about something. Can you check if the augmented PMFs still match to 1?
This?
Yes. Once we have done like those two lines, in the end, I would expect to have a PMF that is still the sum over the second axis. No, the first one. Is it still 1?
Sorry, let me see the target PMFs. Right. Yeah, it's still 1.
After we have redistributed the weights, what does it become? I wonder.
What do you mean, redistributed weights? The target PMFs is the final PMFs that you're going to get, right? After
Yes.
the distributing of the weights.
It's still a correct distribution.
Yes, indeed. And yeah, it starts to make a lot of sense to me. Yeah. So like you said, it's essentially distributing the distributions. I think the naming definitely could be improved. This is terrible naming. If any naming, the B and LU should really give you a sense that it's an index. So what am I trying to say here? Right. So over here it has this L equal to U, which I sort of copy and pasted from one of the implementations. And I wonder, what if I take it off? What's that going to give me? It seems to be in the most parts giving the same thing. But I think the L equal to U is probably handling some edge cases. So in particular, I want to see, is there any 1 here? In the right, there's no 1. Okay. So it's saying if L equal to U. What does that even mean? The cases where the lower bound is equal to the upper bound. Is it saying the case where instead of getting 0.25, you get something like 0, and then the upper bound and the lower bound are the same thing?
If they're the same thing, I think it's exactly the atom, so we can still distribute.
So if we get something like 1 point, and then we say floor, okay, I'll do torch.tensor instead. So that's 1. And then, no surprisingly, its ceiling should also be 1. So I think it's handling some edge cases over here, right? So if your b, one of your b's is exactly an integer, then things are not going to so well. Right. So, right. Okay. I see. So if this happens, if one of the b's is exactly an integer, then what's going to happen is you're going to add 1 to it to minus the b. Right. So if your b is 1, this part essentially becomes 2. And then the ceiling, the upper ceiling is 2 minus 1. I think that's essentially what it's trying to say. And then again, the b1 minus the lower bound is just 1 minus 1 equal to 0. So in this case, it's a perfect allocation to the lower bound, essentially. Okay. I buy
Makes
that.
sense.
Yeah. Well, let me add a little comments. B is 0. Probably say bj to just make sure this is a single component. Example, bj equal to 1, then this upper C should be uj equal to 2 and lj equal to 1. Okay, that makes sense. Okay, I'm very happy. Very productive meeting. I think it makes a lot of sense to me what the distribution is trying to do over here. I'm still lacking a little intuition as to why they do this sort of adjustments, but overall I think it's very good. Does anyone have any questions or comments? Did I lose a lot of people in in the derivation of this part?
Yeah, maybe we'll get to know it when we try to implement.
Yeah.
Yeah.
Ultimately, it's something you have to process by yourself, atom by atom.
Atoms by atoms. Right, fair enough, fair enough.
Kind of.
Yeah, for these implementations, I think it's really important that you implement it yourself and then you compare it with other people. Because if you don't do so, it becomes confusing of what it's actually doing. So Rosalind exactly pointed out B is actually the index, and then everything sort of makes sense from there.
I will also recommend to try it on Cartpole, nevertheless.
Yeah, I did.
Patterns,
I did.
Easier to debug.
I did. With Cartpole, I haven't uploaded yet, but it works with Cartpole. So it's basically the identical code, and you just remove all of the Atari wrappers, and it works. And a funny story. So, well, this printing needs to go. But, right, I was trying to figure out what the UI is. But yeah, so funny story. I was trying to implement, right? And then it doesn't work initially. And I was like, oh man, I look at the training graph, looks like this. I was like, okay, something went wrong and I don't know what it is. And then at some point I realized, oh, I see a lot of 200. And then I see this and I was like, oh, I know exactly what went wrong because I had something that looked like that before. And the reason was because of the linear layer, something wrong with the neural network. And I immediately added some ReLU layers, and then it just works perfectly. So yeah, that's very good. Carpool works. And also I want to give everyone a sort of recommendation, I guess. So recently I stumbled upon this reinforcement learning library that I personally really enjoy reading it as a reference implementation. Well, for the most part, I would say. So one thing to notice right off the bat is that their implementation is benchmarked. And that's exactly one of the things that CleanRL is trying to do, right? We want to provide a benchmarked implementation. Because if your implementation only works for carpol or pendulum, you never know if it works in general. You never know what is the quality of your implementation until you try it out on a variety of games. It's almost like test cases. Can your implementation solve a particular game? And this is something that I really enjoy about this implementation is that they actually give you this. And another thing that I really enjoy is that their documentation actually it kind of goes over on a very high level the design principles and stuff like that, so that you understand what they're trying to do over here. But its design is a little bit interesting. So, for example, the agent, in order to perform an action, you actually need to pass in the state and the reward. So I actually posted an issue in the repository, and the author says, "Interesting, good question," but it's actually the formulation that Richard Sutton and Bartow has used, which essentially, if you look at the graph over here, the reward and state is passed to the agent. So that's why they have the state and reward. I find it to be a little bit confusing, and it doesn't directly work with the gym interface. So you have to use one of the wrappers that they produce to make the actions sort of behave this way. But overall, I find their code to be of high quality, and sometimes it's harder to navigate than others. But overall, very good. Yeah. And I think
Is
they're
that watch beast?
no. This is autonomous learning library, and it's also a work by a PhD student.
I see.
Yeah. So overall, I think it's very high quality. I'm gonna post it in the Slack channel.
I think you already did last time.
Yeah, probably did. Well,
Someone else.
I'm just gonna post it another time over here. But yeah, that's a reason I was motivated to do the benchmark. Just put it in the repository over here to just kind of show similar things. It's much easier to see. Oh, this is a benchmark implementation. Um, so that's also a reason that why I want to sort of spend a little time for the next development cycle to tune the performance, because as you can see in some of the plots, some of the agents are obviously implemented. There's some issues with the implementation. So in particular, we know that, for instance, SAC really shouldn't be performing this poorly. SAC really should be one of the state of the art. If you look at this library's implementation of SAC, so he actually has this part where it talks about the benchmark of performance. I really like this part. He essentially says, for comparison, we look at the results published in the paper and the results matches, which means we're, for the most part, correct. So I want to do that for a lot of the environments that we have as well. In particular, notice the SAC doesn't perform very well, but in their implementation, sorry, this is Atari, but they have something over here. Right, this is the implementation, a benchmark implementation on the PyBullet environment. And as you can see, SAC is clearly a state of the art. So we reproduced TD3 as a state of the art. I was very happy about that. It performs very well, but SAC, we definitely didn't stretch it that far. And overall, there's a lot of issues with reproducing the published results by the paper. So I think maybe the next development cycle, we should spend a lot of time doing that, just to tune everything, make sure that our our algorithm make sure that our algorithm works for a very typical Atari games, work with classical control games such as Carpol or Luna Landers. Then we want to make sure that it also works with PyBullet domains as well. And at that point, I think it's good enough to do a major release to say, you know, our thing is ready for general use for research.
Roger that.
Okay.
Okay. Yeah, so overall, I'm very excited.